Just a review of the notes, pages 12 and 13, and I've already marked in some of these. Okay, so in question 12, or page 12, families of particles, so read down through that, on the line high kinetic energy, and the original particles remain, very important, NB. This is an example, okay, so proton plus proton giving you proton plus proton, both still there, and the additional particles. Okay, and the rest, I think, is pretty straightforward, so read down through it, and the particle zoo, underlined particle zoo. Then we have our two types of particle, the lepton and the hadron. So leptons, elementary particles, same name as fundamental, do not feel the strong nuclear force. That's the most important thing. They do feel the rest, as long as they have a, they will feel the electromagnetic if they're charged. 6 leptons are antiparticles to the electron, the muon and the tau in increasing mass, and the rest. Okay, the hadrons, okay, so you have your mesons and your baryons, okay, and you must know the makeup of the proton, the neutron, and the pion, all just ups and downs. Right, quark model proposed by Murray John Mann, named from James Joyce's Finnegan's Wake. Okay, so this Irish author's novel Finnegan's Wake had the statement 3 quarks from us to mark. A quark was a bark of a seagull, okay, and because it was 3, and at the time Murray John Mann, who discovered it, thought a quark, there were 3 quarks, he used that, he was big into linguistics as well. Right, so we have the, basically we've up, down, charm, strange, top, bottom. So down the bottom here, you're going to put in these two little tables. So increasing mass, up, charm, top on the top, down, strange, bottom. So this is it. Plus 2/3 minus 1/3 is the charge, fractional charge. Increasing mass for the electron, to the muon, to the tau, all charge minus 1, and their equivalent neutrinos. So these are the leptons, these are the quarks, okay, and these are part of the standard model. Right, remember quarks can't exist on their own because everything must have a whole number charge. Remember, the whole number is a charge on the electron, so everything has to be a multiple of the electron's charge. Right, so go forward to page 13. So we have the 6 leptons and the 6 quarks, and then we have the 4 fundamental forces, the strong, the weak, the electromagnetic, and gravitational. So remember, the electromagnetic and gravitational, what we feel, okay, so force between, so all forces we experience except gravitational, put in there, should be in there, force between charges. Okay, and the gravitational force between masses, they're the crucial points. The ranges are infinite, as we've said, okay, they obey the inverse square laws. We will come back to that when we're doing gravitational forces and we're doing electrostatics. So the particles are affected, particles with charge, particles with mass. They can be attractive or repulsive or attractive. So they're the electromagnetic, gravitational, they're the forces that we experience on a day-to-day basis. The other forces are the forces within the nucleus, only within the nucleus. So they have very short range, very small range, okay, and strong nuclear, okay, affects hadrons only, okay, and the weak nuclear affects all particles, okay, and they're both attractive forces. So the weak nuclear force does not, the strong nuclear force has no effect on leptons, and that's the important thing. Important to be aware down here that gravitational has a negative effect on fundamental particles due to their very small masses. So gravitational forces are only noticeable if you have large masses. So with very, very small masses, they are negligible. They're there, but they're negligible. Down the bottom, particle accelerators. So we have these ideas of these cyclotrons, okay. So Lawrence pioneered them in the 1930s, okay. And the Large Hadron Collider is our new version. Okay, it's our most up-to-date version. Huge experiment going on under the ground in Switzerland and in France. Magnetic fields provide a centripetal force to get it to move in a circle. Electric fields accelerate the particles in the same way as for the cathode ray tube, the X-ray tube, and Cockcroft and Walton's experiment. High energy electrons lead to many new particles. Accelerators led to many new particles being found, which was your particle zoo, and it went on from there. That's it.